So I wanted to tell you today about some algebraic tools that we have available to us in the design of optimization algorithms for smooth convex functions. Okay? So everything I say that's going to be my own work is also going to be joint with Ben Grimmer at Johns Hopkins University and Alex Wong at Purdue University. So just to give you a quick outline of what we're going to be talking about today, we're going to be introducing first-order methods for convex optimization. Then we're going to be talking about existing work on minimax optimal first-order methods for these problems. Then we're going to be going sort of beyond minimax optimalities. So this is sort of the new work that I wanted to introduce here in order to talk about a new notion of optimality in algorithm design, which is the subgame perfect optimality. And then I'll go into some of the details, and then at the end, I'll be talking about this long step gradient descent method if there's time left. Okay, so just to give you a quick overview of the kinds of problems we're going to be talking about today. So we're trying to minimize smooth convex functions. So what do I mean by a convex function? This is the inequality that defines convexity and the inequality that defines smoothness. Really, you should think of f as being some sort of bowl-shaped function whose derivative is Lipschitz. So it doesn't change too much if I change the input parameter. Such functions appear in many optimization problems as either sort of measurements of my distance to some target thing, like in linear regression, or as regularization terms to try to smooth out some sort of data-based optimization problem. Now, there have been a lot of work on first-order methods for such convex functions. To begin with, there's sort of a standard result about gradient descent, which says that if I take gradient descent, which I have not yet defined, but I will in a momentarily, then you get a convergence rate of this type. So just to say a little bit about what this inequality really means. So here I have on the left, a term which represents how far away my final iterate is from the minimum possible value of this function f. Here, x star is a minimizer of the function f. And on the right-hand side, I have a bound on the distance between my initial iterate, which is x0, and this minimizer x star. Okay, so intuitively, you should think that if I start arbitrarily far away from where I want to go, which is this minimizer, then I cannot bound my performance very well. But if I start in a reasonable distance to the minimizer, then in fact, I will get a good bound on how far away my function is from its minimum value at the end. Okay. And the important thing about gradient descent is that, roughly speaking, the rate of convergence is like 1 over n. N here is the number of steps I need to take for this algorithm. The surprising work of Nesterov in the 80s showed that, in fact, you can do better using a technique called momentum. Again, I have not defined what momentum is yet, but I will momentarily. And this improves the performance of, or I should say the convergence rate of this method from n, 1 over n, to 1 over n squared, so a much faster convergence rate. And it turns out that up to a constant, this 1 over n squared is roughly optimal. So in fact, people did further analysis of these methods using novel techniques starting in 2014 with the work of Dror and Tabul, showed that in fact you can do a better analysis of even gradient descent, the sort of the most basic method, to improve this constant by a factor of 2. And similarly, the work of Kim and Fessler gives an explicit gradient method, which is minimax optimal. So I will explain what that means also momentarily. But this is just to give you a flavor of the kind of results that we're trying to show here. We're trying to show that some algorithm for minimizing a smooth convex function will give you a good answer in a short amount of time. So these last two works I want to highlight because they use the same methodology that we'll be talking about in the work described today, which is this performance estimation framework for understanding the convergence rates of these types of algorithms.
What constants we improve the
Sorry, so you can see here that standard gradient descent gives you 1/2n. Like this is the explicit number here. Here you have 1/4n. So there's a factor of 2 improvement there. Okay. Thanks for the question. Any further questions? Yeah. Oops, that is far beyond where I wanted to go. Okay, so let me be explicit about this algorithm that was described by Kim and Fessler. So what they showed was that there's some explicit algorithm. I won't tell you exactly what it is because it's a little complicated. But this algorithm is called OGM. And if it's run for a certain number of iterations, it gives you an output whose quality is is given by some number tau n. So tau n is, its true definition is a little messy. You can think of it as being some quadratic function in n. Okay, so they give, again, all of this stuff is explicit, but I'm sort of hiding it for the sake of exposition. So they showed that there is some algorithm which gives you this guarantee. On the other hand, later work of Drury showed that actually this algorithm, you cannot improve upon this constant. So in like a very explicit way, so there is a so-called hard function with the property that any, so these are called gradient span methods. In essence, you can think of these as being any first order method that works without sort of additional assumptions on the function. You actually get a lower bound whose performance is exactly the same as the OGM performance. Okay, so this is the sense in which this algorithm is minimax optimal. I've shown you that there's an algorithm which achieves a certain guarantee, and that there's a function for which no algorithm can achieve a better guarantee. Okay, so does this concept make sense to the people in the room? Okay, so in some senses, it seems like this should be the end of the story, right? There's really no way that you can beat this sort of guarantee. I mean, this is really saying that it's the best possible. But what I'm going to show you in the next slide is that you can actually hope for more. You can actually hope for more, even better guarantees. And this is how I'm going to be talking about beyond minimax optimality. Okay. So just to motivate, like why you might think that something is not telling you the complete story here. Here I have a very simple function. This function is 1/2 x squared. And I'm comparing the performance of vanilla gradient descent, with some fixed step size, and this optimized gradient method. And what you can see is that actually gradient descent will beat out the optimized gradient method on this particular function. And the reason that's the case is that, okay, so actually this function, 1/2 x squared, is also so OGM performs as badly on this function, 1/2 x squared, as it does on this hard function that Drury cooked up. And sort of this is a surprising behavior because you would expect that, if this algorithm is going to perform well on the hardest functions, it should perform even better on an easy function, a function which has a very nice explicit form. And just to make one more comment, so what it turns out is that if you do 2 gradient descent steps on this particular function, and you know that the function is 1 Lipschitz and convex, then once you see those 2 gradients and the value of the function at those 2 iterations, the minimum is actually uniquely located at the origin. So from an information theoretic perspective, you should expect to be able to do better, right? You would like an algorithm that once it sees those 2 gradients, can determine that actually any smooth convex function is going to be minimized at the origin here. So this is sort of the level of optimality that we would like to achieve. We would like to go beyond this minimax optimal algorithm and get slightly better. And the way that we're going to think about like what it even means to do better, how do we understand like how do we improve upon this notion of minimax optimality? We're going to think about this from the perspective of a game. So I'll assume a little bit of game theoretic knowledge, but basically the idea is that there's going to be two players. One player, let's say you are the optimizer. You're trying to look at some sequence of gradients and function values and determine good query points at which you hope the function will be small. On the other hand, your adversary, I am trying to hand you function values and gradients such that it's hard to identify where the minimum is after seeing these function values and gradients. So yeah, in every round, Alice chooses a query point xi, and Bob chooses a pair of values for f of xi and the gradient of xi. And then at the very end of the game, I, meaning Bob, need to declare a function which interpolates through all of these values and these gradients. And also I need to declare where the minimizer of this function is. And then my reward is essentially the ratio of the two quantities that we've been seeing in these slides that tells me how well my algorithm did at the end of the day. So there's this thing called a Nash equilibrium. This is a concept from game theory, which sort of matches this minimax optimality notion that we've already gone through before. What it says is that there's a strategy for this game, meaning that both players know what moves they're going to make, no matter what their opponent does, with the property that I cannot improve my score by changing my strategy while your strategy remains fixed. And you cannot improve or decrease my score by changing your strategy while my strategy remains fixed. So the strategies are, I'm going to choose query points according to this optimized gradient method algorithm. And my opponent will respond with, sorry, I've switched the roles here. So the optimizer is going to choose query points according to the optimized gradient method algorithm. And I will respond by giving you values and gradients from this Drori hard function. And what I've been saying about minimax optimality is really saying that this is a Nash equilibrium for this game. Okay, so neither player can improve their performance by deviating. Now, in practice, you might be playing against like a super genius who knows off the back of their hand what the Drori hard function is, and they will play against you in the optimal way. Okay, you cannot beat such a player and improve your score. That's what we've been saying about minimax optimality. On the other hand, you might be playing against someone who doesn't really know what they're talking about, and they just pick some random function. And in practice, you would expect to have a situation that lies somewhere in between these situations, right? In the real world, you're not given arbitrary function. And what you'd like is an algorithm which is optimal in both of these situations, okay? So even if your opponent is sort of making suboptimal moves, you want to be able to get a performance which is sort of maximally capitalizes upon this notion. So this fellow is Arkady Nemirovsky. He's a professor at Georgia Tech who really was seminal in many of the notions in convex optimization that we have nowadays. And the player on the right is some handsome devil who shall remain nameless. Anyways, so this leads to a game theoretic term, the notion called subgame perfect equilibrium. So this is a little bit of appropriation of the term because they really wanted to model something different when they used this term. But we want to model the following situation, which is that at every stage of this process of this game, I'm going to have developed some number of query points and some number of function values and some number of gradients. And you imagine that at, let's say, some iteration n, those values are locked in place. This is what we call a subgame. So I've already played the game for some number of rounds, and now I'm imagining that this is my new game, right? Starting from this set of data, I need to proceed from there. And a pair of strategies is said to be in subgame perfect equilibrium if for every subgame like this, the two strategies are still in Nash equilibrium. Okay, so let me be more explicit in the following theorem about what exactly it is that I'm going to say about this new algorithm. I'm sorry, I should say, okay, so this OGM algorithm is not part of a subgame perfect equilibrium because on this function 1/2 x squared, a player could have, after seeing two gradient values, already chosen the optimal point. So it's not in Nash equilibrium after the, let's say, the second round of this game. Okay. So the new algorithm, which we call the subgame perfect gradient method, provides the following guarantee. Suppose that I have a sequence of triples, so query points, function values, and gradients, that come from playing this game for some number of rounds. So I choose the query points x0 through xn. Then there exists some hn hat. This is some function of the history of the game so far, such that for any function which agrees with these values and gradients at the query points that have been chosen so far, I have this guarantee. So tau n hat is my payoff for this game. Yeah?
How does little n relate to capital N?
So little n is some, so little n is just some intermediate point, and capital N is the number of iterations this algorithm is going to run. Okay, so capital N represents like my horizon, after which, and my payoff is going to be measured at that point. Little n is like at some intermediate step, but that's smaller than capital N. I've seen some gradient information already, and now I'm going to declare that I'm already going to give you a guarantee at the nth iteration, which, okay, does that make sense? Okay, so yeah, so tau n is the payoff that I'm going to guarantee at the little nth iteration. On the other hand, there exists a hard function which agrees with this first order history, which satisfies the property that any gradient respecting algorithm cannot improve upon the performance of this subgame perfect gradient method. So this is saying that these strategies, so there's a strategy for the function player which makes sure that this subgame perfect method is in subgame perfect equilibrium. Okay, so this is sort of the main conceptual point of the talk, that there is an algorithm which gives you this sort of guarantee. So it's good if someone is not clear about what exactly it is that I'm promising you here, to ask questions about it now.
So this theorem, it shows that these optimal strategies exist. Do you have any understanding of whether the optimal moves are unique?
That's a good question. I think for the hard function, I don't think, like, I think they're not unique. The hard function certainly is not unique, for example. But yeah, I'm not sure about the uniqueness of the algorithm. That's a good thing to ask about.
Just to clarify, the tau n, is that independent of the function that you're minimizing?
Yeah, so tau n is, so the guarantee I'm giving you is that after capital N steps, for any L smooth and convex function, I get this bound, right? So it's independent of the function that I'm minimizing yet. Except insofar as it does depend on the gradients, the earlier gradients. So the first little n gradients, capital or tau capital N does depend on those values. Yes?
So in particular, tau n depends on the root.
Yeah. So So I mean, technically, I should have put tau n of the history. Like it's a function of the history. But I've suppressed that for notational convenience. Yeah, one more question. Yeah.
Just to follow up on that, so how does tau n scale with the history? So if
So
you just one history point, there's a tau n, and then if I give you everything, there's another tau n.
right. So the issue is that it depends on the function that you give me, right? So if you run this on the Drori-Hart function, then this will exactly mimic OGM because no algorithm can do better than that. The tau n at every iteration will simply be the tau n that is guaranteed by OGM. So it's going to be this 1/n squared thing. If you give me the function 1/2 x squared, after, so like tau, let's say 3 or 3 after iteration 2 is going to be infinity, I guess. It will be unbounded, technically. It will have converged by then. Okay. Oh, good questions. Okay, so let me go on to talking about exactly how we derive this algorithm and the methods that we use to prove its convergence guarantees. How am I doing on time? Okay, good. Okay, so the basic idea of performance estimation is that when you look at a function, you don't when you look at these kinds of functions in computer science, you don't really get like a whole function, a whole surface of values. You really only get to see its values and its gradients at a fixed number of points. And you can ask the following question, like, if you hand me a set of triples, so points in, so D is going to be the dimension of the inputs to my function. A set of triples which represent query points, function values, and gradients. We say that the set of triples is interpolable if there actually exists an L-smooth convex function which agrees with those values and those gradients. Okay. And a theorem from 2016 gives us necessary sufficient conditions for a set of triples to be interpolable. It is interpolable if and only if for every pair of I and j, this, it turns out to be a quadratic function of the values and the positions and so on, is non-negative. Okay, so this is like a very explicit set of conditions for this set of triples to be interpolable. So this forms the basis of a technique called performance estimation for proving bounds of this type. So if you imagine your iterative algorithm as defining a sequence of these points, x0, x1 through xn, then we want a bound of this form where tau is as large as possible. Okay? And the sort of maybe a bit of a conceptual thing is that we're not really doing this over all convex functions, but really doing this over trying to make this as large as possible, where we're only thinking about interpolable triples, right? This only depends on the gradients and the function values and the xi's and so on. So the idea for how we can prove an inequality of this type is to write it as a non-negative combination of inequalities which we already know to be true. So here I have a reformulation of my bound that I want to show. So I want to show that this quantity here is non-negative. And I can do that by writing it as a explicit non-negative combination of the desired inequalities. Okay, so if it should be clear, for example, that this thing over here is non-negative because each qij is non-negative, each lambda ij is non-negative. And the equality, by equality here, I mean I want equality sort of as polynomials in xi's, gi's, and fi's. Okay, so one issue with this overall strategy is that this is actually impossible. You cannot literally do this. And it's for kind of a silly reason, but it turns out to be important, which is that the norm of this quantity x star squared does not appear anywhere in this expression. So you actually cannot literally write this thing as equal to this non-negative combination for this sort of trivial reason. But there is a way you can fix that. So what you do is you subtract off this weird auxiliary term in order to cancel out the norm of x star squared. So hopefully you can see now that on the left side here, if I were to expand both of these norms out, the norm of x star squared cancels. And so the thing on the left and the thing on the right both do not depend on the norm of x star squared. But in order to do that, I introduce a new vector z capital N, which perhaps you are wondering what is this thing. I haven't told you what it is yet. It doesn't actually matter. If I can write down this expression, if I can find these lambda ij's that makes this true for any zn, then you've proven the inequality that you want already. It happens that this zn has an interpretation. It turns out to be, roughly speaking, the momentum. Okay, so this is I guess an algebraic interpretation of where does the idea of momentum sort of come from in these proofs. This is obviously very ahistorical. I think Nesterov just had the idea of introducing momentum, but you can imagine that if you were trying to do all of this stuff starting from this notion of interpolable triples, you might arrive at this conclusion yourself. Yeah, so this slack term is exactly what's needed to work for this thing to work. I've done out this example in the case of gradient descent just to make sure everything is very concrete. So here my algorithm is simply going to take one step where I set x1 equal to x0 minus this multiple of the gradient of the function. And this g0 here is going to be the gradient of f at x0, and g1 is going to be the gradient of f at x1. And you have this list of inequalities, which you know to be true, because the function is L-smooth and convex. And just to be even more explicit, you can substitute in the value of x0, and you can start to see that maybe some of these things cancel. You can give this to a high school algebra student and ask him to show that actually when you add up these three inequalities, you get, or really these are three polynomials, you get the desired inequality that you want. This certifies that one step of gradient descent provides you with a bound of an upper bound on your suboptimality, which is like L/2. So tau here is equal to 1. Okay, so does this example sort of make sense to the people in the room? Okay. Okay, so now I want to go into how you can derive momentum methods using the framework that we've built up so far. So again, what we're trying to do is we're trying to prove an inequality of this type. If you can show that this is non-negative, then you've shown that your algorithm converges at a certain rate. And you can imagine that at maybe some iteration prior to your current iteration, you've already gotten this hypothesis down, right? You've somehow managed to write this quadratic polynomial hn-1 as a non-negative combination of my qij's. That's sort of the strategy that we're going to be undergoing here. We would like to now produce an inequality of this form. We would like to show that this hn is non-negative for some value of zn and some value of xn. Okay, so I don't, at this point in the algorithm, I don't know where my next iteration is going to be, and this is what I'm going to try to figure out now. Okay, so I'm trying to get this inequality, right? Does this make sense? Okay, I'll skip over a little bit. So it turns out that what you want to do at the end is to write down an expression of this type. Okay, you want to express the next step of some sort of inductive strategy for proving this inequality as a weighted combination of my earlier inductive hypothesis, the thing that I've already proven, plus some combination of these QIJs, which turn out to, you only need to choose from these three. And the sense in which I want this to be inequality, and this is I think a little bit of maybe a minor conceptual insight. As I want there to be an inequality as a polynomial in these four variables. So it's important here that at iteration n-1, I've already chosen the first n-1 iterates of my algorithm. So I don't get to I already know what those are. Those are some constant numbers that are sort of floating in space at this point. But I don't know what these numbers are, and we need to make sure that whatever next step we pick, whatever next step we pick, these numbers remain under control. And there's a sort of miracle that happens here, which is if you count parameters. So there are 5 of these quantities which turn out to be scalar numbers that you need to be equal on the two sides of this equation. You also get 2 quantities which are vectors, which you also need to be equal on the two sides of this equation. And it turns out that you get exactly the same number of free parameters once you've chosen this sort of inductive setup. So you get to choose your set of coefficients, you get to choose your next iterate, and you get to choose your next momentum. This should have been Zn. Okay. So in principle, there should be a single solution, or rather a finite set of solutions for that actually makes all of this work. And it turns out that, okay, you can get Mathematica to solve the system for you. This is how you do it when you're not undergrad, I guess. And then you get this lovely set of parameters. And what exactly these are is not so important. It's just that the important thing that you need to understand is that I did not have any choice in what this xn is and what zn is. Okay, these all come as necessary consequences of this sort of strategy for proving this inequality. I can solve for them in a sense once I know what it is I'm trying to solve for. And this turns out to be a variant of Nesterov's original fast gradient method. And he did some slightly different things in order to make sure that actually these update parameters were some constant numbers. But what exactly that is not so important. The important thing is that, okay, this overall strategy does work, and it does sort of recover stuff that we've already know how to do. So the overall conceptual things I want you to take away from this are that you want to prove an inequality of this form by induction, and you do that by writing the next inequality of this form as a non-negative combination of your previous inequalities and the interpolation conditions. And then once you have this setup, once you know what it is that you're trying to do, there's a unique choice of xn and zn that actually makes this overall proof strategy possible. And so now I wanted to take us to how you derive this optimized gradient method that I've already talked about in some length. And the idea is that you can somehow make an improvement to this strategy by slightly modifying the inductive hypothesis. You change the inequality that you want to prove a little bit. Now it turns out that, okay, now you might say, okay, but even if this is true, that might not necessarily prove the inequality that I want, because now I'm adding on this non-negative term. It turns out that you can fix that by taking a single ordinary gradient step afterwards. So it turns out not to be so important that I've added this extra term. But it turns out that once you do that, you can do the same overall strategy, right? I haven't really changed very much about this problem setup. And so again, I'm able to solve explicitly for what xn is and zn is. given that I'm going to be using this framework for proving my convergence rate. And this turns out to give you this optimized gradient method, which we've already seen is minimax optimal. Any questions about the derivation up to this point? I think there's it's easy to like look at these things and be like, oh, this is a horrible, nasty equation. The actual values here do not matter at all. The only thing that's important for you to understand is that once you have the proof strategy in mind, which is, I think, very natural to try to write some non-negative quantity as the sum of some other non-negative quantities, then in fact there's only one algorithm, which you can explicitly to figure out what it is, that makes that overall proof strategy work. Okay, and this is somehow the thing that we're going to do to get this subgame perfect optimality. And the idea here is essentially that, so the algorithm that I just mentioned, optimized gradient method, only considers your current iteration, your current momentum, and your current gradient. The idea is really going to be that we're going to remember more history. So we need to keep track of a lot more memory. And in return, we get some improved performance. So we need to remember all of our previous gradients and previous momenta. I mean, really, you only have to, you'll see in a second that actually you can get different algorithms depending on what it is exactly that you remember. But I mean, the overall idea is exactly the same. So we want to write the next step of our inductive proof as a non-negative combination of things we already know to be non-negative. And essentially, everything else stays the same. Except now we have actually more free parameters than we have equations. So it turns out that the number of equations that we need to satisfy stays the same. It's still these 5 scalar equations and 2 vector ones. But now we have a total of n degrees of, maybe 3n degrees of freedom, right? I'm allowed to choose these coefficients now however I like. So there's some optimization problem here that we need to solve in order to make any of this work. But then here's the surprising thing is that you can actually solve this optimization problem. It turns out that once you go through this process of equating coefficients and so on and so forth, you get a very simple set of constraints and a simple expression for what tau n is going to be in terms of my weighted coefficients. And you get a kind of optimization problem called a second order cone program. And these are things that, okay, maybe I'll pause for a second and say a little bit about something that's funny here, which is that so I said that we're going to try to solve a convex optimization problem, which is minimizing a convex function. And now I've told you, well, now we've reduced it down to solving what might be a more complicated optimization problem. The things that are important about this optimization problem is that secretly, the size of this optimization problem is only scaled with the number of iterations that I take. And typically, when you do these modern convex optimization problems, you take the dimension of the input to your function is much larger than the number of gradient steps that you take. And so it's not entirely unreasonable that you might want to take some more time in terms of which only scales with the number of iterations, which might be small, in order to get a savings on your convergence rate, which in principle might scale with dimension. Okay, any of these questions?
By nature of this being a SOCP rather than an STP, this should be pretty fast to solve, right?
Yeah, it should be.
Could you give me a sense of scale? Like I know.
Yeah. Okay. So
the key is like 1,000. Is it like milliseconds to solve? Like it is.
Yeah, I think if you use MOSEC, which is what we were using, I think it. Yeah, I mean, so I'll show you some benchmarks, but I don't think that takes. You could probably, yeah, probably like maybe on the order of milliseconds, maybe tens of milliseconds to solve a problem like this.
And D and G, these are very
So
smart
yeah,
things.
no, sorry. So these are matrices. So G is just the matrix whose columns are gradients, and Z is the matrix whose columns are momenta. I think so. Part of, but I think that the algorithm that we're currently using to solve this subproblem is a little bit pessimistic, just because the problem actually, you basically introduce two new variables at every step of the algorithm, and you update this matrix by adding a new column. There's a lot of work that's been done on online linear regression, where you essentially update a linear regression problem by adding in new data points at every iteration. And you can solve, the amortized cost of solving those things is typically much smaller than sort of resolving the whole thing at every iteration. So I think that there's a lot of structure here that we're not currently, or we haven't really looked into exploiting. There's also sparsity structure in these coefficients. I think actually it turns out that you can probably figure out exactly what the support is, in which case it becomes a linear regression problem, which is, of course, very easy to solve. And so I think that I'll say that I think this problem is maybe easier than it looks at first glance, but I won't promise that.
One more question of clarification. So this is the player, the optimizers solved, or is this solved by the adversary?
This is solved by the player. So you, if you want to run this algorithm, you do need to solve these problems at every iteration, which is, oh, right, sorry. So I think that right. So yeah, the overall runtime of running this SPGM method on the problem of size like 1,000 would be on the order of maybe a second. So I would expect that this individual problem, I don't know exactly how long it takes, but maybe, yeah, on the order of milliseconds. Yeah, and so just in case anyone is curious, these are how you then update your X's and your Z's. So you can see that it's some very explicit expression in terms of the optimization problem that we've already solved.
So are you only using the optimal value? So once you solve the previous problem,
yeah.
Are you only using the optimal value?
Yeah.
Okay, so the optimal mu lambdas, you don't.
Yeah. Oh, sorry, no. You need the optimal mu's and lambdas. Sorry. Yeah. Those go there. You don't just need them. So it turns out that the optimum value is going to be this phi n value. But you do need the variables as well. Yeah.
The subproblem that you mentioned, or like if it's like not solved like perfectly,
you still get a bound. So as long as you have any feasible point gives you a bound, and you can be very explicit about what the bound even is. Okay. Yeah. So you could solve it to some order of accuracy. You won't get the subgame perfect guarantee anymore, but you will get, in principle, faster convergence than if you just ran it with optimized gradient method. In fact, the optimized gradient method can be represented as a feasible point inside of this larger optimization problem. And so that means that this always does better than the optimized gradient method at every iteration. Okay, yeah, these are just some slides that indicate the numerical performance. You can see that it does. Okay, maybe you can't see because the colors are really bad. This is SPGM. This is OGM. I guess this is gradient descent. Yeah, so these are just some random problems. You can see here maybe that SPGM really converges in like I don't know, roughly 300 iterations. It's pretty much hit like machine precision. This pink curve is BFGS, which is a different algorithm which also remembers your history of gradients.
Sorry, is that OBFGS or?
This is LBF. I think this is, so we ran an LBFGS, but it might have been with full memory. I don't actually remember what exactly it was in this picture. Yeah, and here's the same thing for subgame perfect gradient method. Yeah, so you can see here that on medium accurate, if you want medium accuracy, SPGM is outperforming BFGS, let's say.
I guess since you know, you're talking a lot about how they're going to get very different performance for some of these algorithms depending on the function. Like, it's like what functions were used for?
Yeah, so we used a mix of so there are some real world optimization problems that you can find in like repositories on the internet. So that's what we were using on the bottom slide. The top slides are random instances that come from like very simple families of problems like quadratic functions, like these things called log sum x functions, logistic regression problems. These are the types of things that you're solving. What's the random ones?
So the high-level takeaway of these 6 figures is that OGM is always very bad. And
OGM is, yeah, it's not very good. Gradient descent, I think. Wait, shoot. Sorry, I need to look at my actual slides to see which one is gradient descent.
both the color and the projector.
Yeah. Yeah, sorry. Yeah, I think gradient descent will frequently actually outperform, right? So this guy here is gradient descent, and yeah, this guy here is OGM. It's you can see that it's yeah, I guess OGM does pretty badly on these instances.
Was there any, have you tried just using Nesterov? Was there any, you know, if there's any?
Oh, we didn't try you just using Nesterov. That would be good to add to these plots.
Yeah, I think people might be curious if there's a difference.
Yeah. All right, I think that's pretty much all of my time. I did have some more slides about some other work, but I think I will not get into that for the sake of time. So that is right. So I guess the last thing I should say is maybe how you construct these lower bounds. Essentially, you take this optimization problem that we solve in each iteration and take its what's called its dual program. So the dual program gives you a way of explicitly constructing upper bounds or lower bounds for the optimization problem, and you can use those parameters that you get from the dual program in order to come up with a set of triples, which you can then interpolate a function through and improve this type of thing using some existing technology for how to prove these such lower bounds. Yeah, so I think that is all. I'm happy to take any further questions now.